What? Oh. No, it's not. So I got 79. Is it seriously 78 in your book? Oh, you're right. Okay. Now are you there? Okay. So, before Newton, I know it was a while ago, but there were people that actually existed before him.
Really?
Yeah. And one of them was a guy known as Kepler, an astronomer. That might be him, yes. He investigated planetary motion, came up with some laws, which, who knows, maybe some of you guys will investigate them. But one of which is, that's supposed to be an ellipse. That would be the sun. And this would be what we call a focal point for this planet going around the sun. So in other words, if this was a mirror and I put a flashlight there, it would reflect all of its light straight out. In other words, all this light, if this was a mirror, could come in and collect all these rays right at that point. And that's kind of cool if you're outside in the sunlight and you have some bugs around. So then you can make it burn. But anyway, it's the story about Newton. First things, I don't know how you kids know this, right? Because you know Newton and you know the story about this apple. And most of you know that before you came here, right? That's kind of, is that in cartoons? Like, I can't remember myself. I probably knew it too. You just know. So here's some bad tree, and here's the story of this apple. Kepler knew that, you know, all our planets, I mean, I don't know. It's amazing if you think about it, but they keep going around and around and around. How many hundreds, thousands, millions, billions of years? And not one has hit the other one yet. And there's quite a bit of stuff going around, right? It's not just the 9 or 10 planets, depending on what year you count them. Jupiter's how many moons? Like 21, I think. They keep going around Jupiter, and it keeps going around, and they all go around the same direction except, what's the one? Uranus? It does the opposite thing, goes in the opposite direction. Okay, I don't know why, but anyway. Kepler studied this stuff. Okay, Newton took it one step further, and he just said that all these planets are attracted to each other, but it's not just the planets. It's every mass is attracted to any other mass. That's his universal law of gravitation, or Newton's law of universal gravitation. So, this apple is attracted to the Earth, but vice versa. The Earth's also attracted to the apple. So you guys know what happens, right? When this apple breaks off the branch, the Earth comes up and hits the apple. Is that incorrect? Yeah. How do you know? Well, how do you know? I've seen it happen. The Earth comes up and hits the apple. So that the next picture is, here's the tree, the apple's sitting right there. Earth came up and hit it. When we get to relativity, this will make sense to you. So anyway, here it is. Newton's law of universal gravitation. Does that look like a big Jim Dandy? It's more a calculator exercise than anything, because a lot of those numbers are really, really big. One of them is really, really, really small. Okay? So every body in the universe attracts every other body with a force that's directly proportional to the product of their masses, m1 times m2, and inversely proportional to the square of the distance, i.e., r squared, the square of the distance. Now I know you want to think that's a radius. It can be, but the correct way of saying it is d is the distance between the centers of the two bodies we're talking about. Okay? So, to clarify, if you're on Earth, and we're going to magnify you really, really, really big, if I want to know, what does FG stand for? Force of gravity. We got another formula last day for this, didn't we? Okay, now you got another one. The force of gravity between two masses. Here's Earth. Here's you, right? There's a force between you. That's why you guys are all stuck in your chairs right now, because there's a force of attraction. We will say for R, that's the distance between your center of mass, which is like pretty much kind of here-ish, and the Earth's center of mass, okay? So that is R. But we can kind of ignore this distance from your chest to your feet when we're talking about this is the radius of the Earth, right? So essentially, all you need for the distance between this you and Earth is the radius of Earth. But don't confuse this being radius of Earth, because now if I have two different planets, the center of mass of one to the center of mass of the other, that's what we're talking about when we say R. Now if I told you the distance between these was, say, I don't know, 1 times 10 to the 10 meters, is that what you would use for the distance between them from their centers of massers? Did I say that right? Massers? No. If I give you this distance, R is that plus this radius plus this radius. Okay? R is the distance between the centers of the two bodies. In this case, it's okay to think of it as the radius of Earth. But R doesn't stand for radius. It stands for a distance. Okay? Here, I would need to add this radius of that planet plus 1 times 10 to the 10 meters plus the radius of this planet. Or I got the question wrong. Okay? That's what this says. So there's a force there between two masses. They could be big, like planets. They could be really, really, really small, like golf balls. Okay, now this is just something to note. This fellow named Cavendish came in after Newton. This is what Newton theorized, but there's some constant in here. Okay, he didn't know what it was. Cavendish figured this out using this contraption. 2 lead balls, a couple other balls on a piece of string suspended in his garage. I don't know, actually he probably didn't have a garage because they didn't have cars back then. I don't know, in his horse stable, in his basement. He actually figured this thing out, okay? He actually got that number. 6.67 times 10 to the minus 11. That is big G. Don't confuse it with little g. Little g is our gravitational constant, depending on the acceleration of the planet, right? Gravitational field strength. This is big G. It's just a number. That's what goes in here. And I'm looking at this, and they're telling me this is how it happened, and I still kind of shake my head going, how the heck did he do that? I don't know. It's not like, is it 10 or is it 50? I did an experiment, all it came out to 10. This thing's 10 to the minus 11. How on earth do you do that with a couple of balls of lead in your basement? I have no idea. But anyway, he came out with this constant. He Googled it. Yeah, all right. Okay, so last day, I told you the force of gravity was equal to the product of a mass times the gravitational field strength. This force is going to be bigger on Earth than it's going to be on the moon, even though the mass stays the same, because g, that acceleration is going to be a lot less, right? Well, here's another formula. So this is Fg, that's Fg. Why don't we say that this mg, this Fg, is equal to g mm over r squared, because they're both force of gravity. So yeah, let's do that. One of the masses cancels out, and what we're left with is this, which I don't believe is on the back of your book, but I may put that on a formula sheet for you when we do our test. Okay? That's another way to calculate the gravitational field strength, little g, given a mass and given a radius. Okay? So, a couple questions. The constant g in the law of universal gravitation has a value of that. We're telling you that's what it is. Nothing you have to memorize. Here's our formula. Some use big M, little m, and other books use M1, M2. It's all the same thing. And I said it earlier, but let's just point it out. This is known as the inverse square law. Okay? Square of r, 1 over it, that's an inverse of the square of r, so it's an inverse square law. Okay, calculate the force of gravity between a 100 kilogram person and Earth. Earth's radius is this. So I already drew you a picture of this, didn't I? What's the distance between their centers of masses? You can ignore the half a meter that you have. Essentially, this is r. But like I said, that's not a radius. That's the distance between the two masses. Okay? So, plug the stuff in. That's g. It's just a calculator exercise. 1m is the person in kilograms. This one's also in kilograms. That's how we want it. Okay? Because that's how this constant works. You notice it's Newton meters squared divided by kilograms squared. So if that's kilograms and that's kilograms, that cancels out. The r squared, if it's in meters, cancels out. And what are you left with? A Newton for force. Okay? So just make sure it's in kilograms and meters, and we're all good. The radius, 6.38 times 10 to the 6, but don't forget to square it. What happens if I don't put brackets there, boys and girls? You get the wrong answer. Okay, you should all be plugging this in to make sure you know how to use your calculator, because this is big ugly numbers, and I see lots of kids make mistakes. So how do you put in 6.67 times 10 to the minus 11? You can put it in like that, but I like to put it in just like the calculator likes it. Okay, 6.67, second function. Here under the comma you see EE. I don't know why it says double E when it comes out a single E, to the exponent of negative 11. Whoop, negative 11. Okay? Times 100 times 5.98 to the exponent of 24. If you want to go times 10 to the power of 24, be my guest. Okay? Divided by, so let me do it wrong first. Oh, it worked. That is the answer. Well, yeah, maybe. If you put times 10 to the, it won't work if you don't put brackets here, okay? But with the exponent it does. So I stand corrected. I thought it would give me the wrong answer. Okay? Okay. So that is the answer in what units? Newtons. Let's think of our other formula. Fg is mg. What is 100 times 9.8? Well, I should get the same thing, shouldn't I? Okay, they both work. 100 kilogram person and the moon. Force of gravity is, again, G. Okay, you don't have to write out all the units as long as everything's in kilograms and meters. Should this force be greater than the Earth's or less? Less. Okay, so this takes me a while when I got to double tap everything. I'll bracket it just to make sure. Squared. Is that less than 980? Sure it is. 162. Okay? So not so bad. Like I said, it's just a calculator exercise. Did you know that two golf balls do attract each other? Do they have gravity? Sure. Not very much, but it's not zero. Okay, notice the units. How do you make that kilograms? Divide by 1,000, move the decimal 3 spots, 1, 2, 3. It's the same mass, so I'm just going to square it. 0.046 times 0.046, right? 10 centimeters. Is that the unit I want this in? What do I want it in, Lewis? Thanks, Jeff. So 10 centimeters is how many meters? Yeah, 100 centimeters in a meter divided by 100. 0.1, don't forget to square it. That times 0.046 squared divided by 0.1 squared. It's pretty small, but it's not zero. (1.4 times 10 to the minus 11). What's the units? Newtons. Is that why when you drop 2 Cheerios in a bowl of milk, they always come and touch each other? Yes. You're going to try that when you get home, right? Okay, I saved this one for last for a reason. It's more theoretical. There's no numbers here, but the understanding is sound. Given 2 small chocolate-covered candies of mass m and m, what will happen to the force of gravity if r is doubled? This is knowledge of the inverse square law. What does that mean, inverse square? Well, f of g is g, 1 big M, 1 little m. What happens if r is doubled? So here's what you can do. I know g is the same in both cases, right? What's a nice value I can use for a mass? There's no mass here. Let's go, do I want this in grams? Let's say it's a big M&M. 1 kilogram, right? And I'll say the other one's the same size. All right, and that doesn't change just because the radius is doubled. G is the same in both cases, so I can kind of get rid of that. What's a nice radius here I can play with? 1 meter. Sounds good. What's 1 squared? So in this case, if they were 1 kilogram each and a distance of 1 meter apart, what would the force here be? 1 Newton. Now let's double r. If this was 1 meter, this is going to be 2 meters. And this force is going to be, what's this compared to that? 1/4 as much. That kind of makes sense? If you bring them farther apart, I get less force. Okay? But if you double r, it's not half the force. Because of the square part, it's 1/4 of the force. There is a point that we assume it's infinite, but no. Yeah, everything's attracted to one another. And this galaxy is attracted to that galaxy, and so on and so on. And according to the Big Bang Theory, the whole universe is still expanding, but it is slowing down because gravity is wanting to, And let's take this one step further. At some point, this whole thing's going to stop, get attracted to everything, every galaxy, and there's millions of galaxies, and then, boom, another Big Bang. And how long has this been happening over the millenniums? We don't know, but we assume it's happened several times. Meryl? Well, because there's G here and a G here, the G doesn't change. It's just a constant. So when I compare these, I can just get rid of it, right? I can ignore it. So, all we need to think about, here's the other thinking, Fg is just proportional to the inverse square of the distance. So if r is doubled, if r was 1, my force would be 1. What happens if r is doubled? I get 1/4 the force, right? The closer these are together, then the higher the gravitational force between the two masses. Further you bring them apart, the less. Yes, that's not gravity, that's magnetism, but yes, same principle. Is that the inverse square law? What if r is tripled? What happens to the force of gravity if r is tripled? Well, how does this compare to that? This is 1, this is, it's 1/9 as big, right? Now let's move them closer. What if r is reduced to 1/2? How does this compare to that? This applies to everything in the brackets. How many quarters go into 1? Down in the Lewis. Stop. If you half the distance, the gravitational strength will be 4 times. Okay? What happens if I third the distance? 9 times. All right? So yeah, you don't like it because there's no numbers here, but that's the inverse square law, theoretically based. So one last thing. Based on this, I actually heard this from my Physics 11 teacher back in 1952. And if there's a guy and he is traveling towards a black hole, the closer you get, the force here is going to be a lot larger than the force here. So the closer you get to it, the more proportional this force here will be larger than that one. And because it's a black hole, which incredible, immense gravity, that of which you've probably heard this before, even light doesn't escape it. That's why they call it a black hole. It sucks in everything with mass, even photons, which is light. What happens is this force overcomes your own body's strength to hold itself together. So your feet become detached from your knees, and your legs become detached from your torso, and so on, and your neck becomes detached from your head. So if you guys are ever drifting towards a black hole, don't go in feet first. Where does it go? Where does it go? It joins this.
Where does that go?
It stays there. What do you mean, where does it go?
You go into the hole. What's in the hole?
That's the trick question, isn't it? We don't know. Okay, if you got the old book with the red bar on the front, because the questions are different, you do that. If you got the new one with the yellow bar, you do those. Okay? They're the same questions, it's just different numbers.